Hi everyone, I'm Ming from Huazhong University of Science and Technology. I present Motor, enabling multi-versioning for distributed transactions on disaggregated memory. The cloud data centers have insufficient memory utilization. It's about 20 to 60%. A major reason is that existing data centers consist of monolithic servers. Each server statically couples some compute units and memory modules. However, different workloads can have dynamic resource requirements leading to unbalanced resource usages across servers. Resource coupling is a key idea to bridge this gap. The disaggregated memory, or DM, decouples the compute and memory resources from monolithic servers to independent resource pools, so different applications can allocate resources on demand, thus improving the utilization and elasticity. The pools are connected using fast network, such as RDMA in our system. To ensure correctness for applications running on DM, distributed transactions are required to provide atomicity for operations executed by the computer nodes, and guarantees the data consistency and reliability in the memory nodes. Transaction is a programming abstract. The operations inside a transaction are completed in an all or nothing manner. This is useful to hide the concurrent excesses and failures. When the data are stored on different nodes, the transaction becomes distributed. A coordinator is leveraged to process the distributed transaction through the network, and various protocols are involved to guarantee isolation, atomicity, and availability. This is the execution model for distributed transactions on DM. The computer node generates coordinators. In our implementation, a coordinator is a coroutine. The memory node stores user data, and these data are replicated into primary and backups for high availability. When processing a transaction, a coordinator reads remote data, executes the logic, and writes the new data back to remote memory nodes. The data access is implemented using one-sided RDMA, which means it does not involve the CPU of the remote node. Moreover, a computer node has a small cache for metadata, such as remote data addresses, to facilitate RDMA reads. A memory node has a weak CPU for initialization tasks, such as network connection. These weak CPUs are not involved during transaction execution, so the memory nodes do not have local compute power to frequently handle substantial tasks. This architecture change calls for new system design to efficiently process distributed transactions. Existing study has supported distributed transactions on DM. It adopts single versioning, so each data has only one newest version. This simplifies the data store, but has two limitations. The first is limited concurrency. Here, a transaction 1 reads two data, and if one of them is modified by another concurrent transaction, transaction 1 will be aborted due to version change. The second is high logging overhead. To provide atomicity, a coordinator needs to write a log to a memory node to back up each written data. This doubles the network resource consumption. Multi-versioning can address the limitations of single versioning. Multi-versions means that storing multiple versions of each data. It allows more concurrency, since the read request can obtain the historical versions, while the write does not remove the old versions of data. It also reduces logs, since the old versions naturally act as undo logs. However, existing multi-versioning distributed transaction systems are based on monolithic servers. They do not fit DM for two reasons. First, they leverage a linked version chain to link different versions in order. The version information and data value are stored together. The chain structure works well in monolithic servers, because each server has CPU to do the pointer chasing to search local data, and it can also easily add or delete versions. However, this structure becomes inefficient on DM, because each local pointer chasing is translated to a remote read. As the number of chain work steps increases, the RDMA read latency grows linearly. On the other hand, the transaction protocol in prior systems frequently consumes the CPU in each data node to execute substantial tasks. Unfortunately, this is not compatible with the weak CPU in memory nodes. To address the limitations of existing studies, we introduced Motor, which enables multi-versioning for DM. Motor has two parts. One is a consecutive version tuple structure as a memory store to efficiently organize different versions of data in the memory pool. And the other is a one-sided RDMA-based MVCC protocol that coordinators can use in the computer pool. Let's first look into consecutive version tuple, or CVT. In the memory pool, motor separates the version information and the data value. Unlike linked chain, CVT stores the version information of a data together in a contiguous memory space. So a computer node only uses a single round trip to read a CVT and then locally looks for the target version according to the start timestamp. This eliminates chain walking. Each CVT contains a header and multiple version cells. The header contains the address of a data value, and each version cell stores the version number and the storage location of the modified attributes. Multi-versioning increases memory usage. To mitigate the memory overhead, we observe that a transaction often updates several attributes of a row. So it's unnecessary to store a full-size value for each version. Instead, Motor maintains only one full value for the newest version, and for the historical versions, we only store the attributes that are actually modified. This effectively saves the memory space compared with storing a full value for each version. In fact, the number of versions to hold in a CVT is dependent on the workload characteristics. We find that two factors dominate, including the read-write contention and the number of records to read in a transaction. If the contention is low, such as in the TATP workload, two versions are sufficient. If the contention is high, such as in the TPCC workload, we need to reserve more versions to allow more reads to succeed. However, if the transactions need to read many records, like in the TPCC case, we cannot set the number of versions to be too large, because a large number of versions enlarges the CVT size, which in turn causes high read latency, and it will negate the benefit of reducing aborts, leading to performance degradation after we reach the peak throughput. When a CVT runs out of space for new versions, Motor performs garbage collection to reclaim old versions. To determine which versions to delete, existing monolithic server approaches involve tracking transaction states. But this tracking is often too expensive for the weak CPU in the memory nodes. On the other hand, if using computer nodes to track, we need a read queue for each CVT to indicate who is reading. This can skip the versions that are being reused, but unfortunately incurs high synchronization overhead to maintain remote states. To avoid tracking, Motor enables the coordinators to actively perform GC by preemptively overwriting the oldest version in the CVT. This is feasible in our scenario because the RDMA accelerating transaction processing, so the oldest version has the least possibility to be used in the ongoing transactions. And results show it does not lead to many aborts. After GC, the versions in a CVT are not sorted, but it does not affect the correctness because the computer node fetches the CVT into local and looks for the target version. In the presence of GC, one transaction may read data being reclaimed, leading to potential corruption. For example, coordinator 1 reads a CVT and decides to read a value at version 1, while another coordinator performs GC and updates the full value. This can result in coordinator 1 reading a corrupted value, because the version and value are not read atomically. To address this issue, Motor wraps each of the VCL and value with anchors. When writing data, the coordinator sets all four anchors to be the same new value, and readers then check if the anchors are equal to validate that the fetched value and the version match. Based on our CVT structure, Motor designs a one-sided RDMA-based MVCC protocol that fully bypasses the weak CPU of memory nodes. Consider this read-write transaction on the right hand. A coordinator first uses RDMA read to fetch the CVTs from the primary replicas each time when the transaction logic needs to read data. For the data that will be updated, Motor locks their CVTs while reading them for exclusiveness. This is implemented using RDMA class. After obtaining the CVT, the coordinator determines the target version that is close to its start timestamp. Then the coordinator reads the full value and any required attributes together, In the worst case, it takes 2 RTTs to read any version of the data, and there is no overhead of writing remote logs. Also, if the data is very small, motor can just store the data together within the version in the CVT, so it only takes 1 RTT to read a version and value. However, if the data is large, it's better to separate value from version to avoid transmitting unnecessary values. After obtaining all the data, the coordinator executes the transaction and uses the commit timestamp to validate that the versions of read-only data were not changed. This provides serializability, but if the application wants snapshot isolation, motor turns off the validation. Finally, the coordinator writes the new version, value, and modified attributes to all replicas and unlocks the write set. Compared with existing systems, motor's MVCC protocol delivers benefits of multi-versioning and only consumes a small number of RTTs. Our testbed includes 3 memory nodes and 1 computer node interconnected via InfiniBand. The workloads include a KV store as a micro benchmark and 3 widely used OLTP workloads. Each table in each workload is replicated into 1 primary and 2 backups in different memory nodes. We compare motor with FarmV2, a multi-versioning system using a linked chain, and Ford, a single version system for disaggregated memory. We first use KV store to compare our CVT with the traditional linked chain structures. CVT achieves the highest throughput in different skewness and read-write ratio tests. This is because CVT constantly requires 1 RTT to obtain the target version, while the linked chains require more RTTs on average to traverse the chain until the target version. We then compare the end-to-end performance between motor and FarmV2 and Ford. Results show that motor achieves high performance. Note that Ford exhibits lower median latency in TATP workload, since 70% of the transactions only read 1 data. In this case, single versioning can achieve lower latency. However, as the transaction's write set grows and the processing logic becomes more complex, the multi-versioning approach delivers more benefits by improving the read-write concurrency and eliminate writing remote logs. Compared with FarmV2, our motor achieves higher throughput and lower latency, mainly because FarmV2 needs to do the chain walking while motor does not. Moreover, motor supports recovery for both coordinator failures in the compute pool and replica failures in the memory pool. The recovery time is a millisecond scale. You can find more details about failure recovery in our paper. In conclusion, this work aims to address the problem that existing multi-versioning distributed transaction systems do not fit DM. We propose a motor that shows a way to leverage CVT to support multi-versioning for DM. Results show that motor delivers high performance and low memory overhead. Thank you for your listening. I'm happy to take questions.